Hi, I'm Hannes,
Hello, I'm Dominic.
and today we have Vijay Dwivedi presenting his paper Graph Neural Networks with Learnable Structural and Positional Representations. And don't forget that you can also join these reading group meetings yourselves via the links in the description.
Hello everyone, my name is Vijay Prakash Dwivedi and I'm a third year PhD student at NTU Singapore. I'm advised by Prof. Antoine Du and Xavier Bresson. I work in deep learning for graphs, and recently my research interest is in having good positional representation and kind of approach for GNNs, and also trying to unify transformers and bridge understanding from both of these fields. So today I'll present my recent work, Graph Neural Networks with Learnable, Structural, and Positional Representations, which is jointly done with Antoine Lu, Thomas Laurent, Yoshua Benjo, and Xavier Bresson. And so let me start now. So before starting, the introduction summary of this work is, so what is the problem that we tackle and what is our approach? So I'll briefly, in a minute, I'll try to say this before going everything in detail. So the problem we tackle is graph positional encoding, and in particular, nodes in graphs do not have canonical positional information like words have in sentences. So this causes limitations such as the lack of global structural information when message passing GNNs, the most popular GNN models, they learn on graphs. And as a result, these kind of models exhibit low representation power and have several issues due to their inability to differentiate simple graph symmetries. This is well known now, but this is the broad problem that we tackle. And our approach in this work is to propose an architecture that we call LSPE, which means Learnable, Structural, and Positional Encodings. And as from the name, this approach helps to be used with any message passing GNNs. And at every layer, it allows learning of positional and structural feature representations separately and at the same time, effectively thus capturing the two properties and tuning these with respect to the tasks. So this is the short summary of the work. And the outline of the presentation will be, first I will show the context or motivation of this work. It will be followed by the background of three research areas that are working towards building better GNN architectures. And I'll then introduce the architecture, LSPE. It will be followed by the numerical evaluations and the insights that we obtain. And finally, I'll conclude with what are the different things that we learn out of this work. So for the motivation, I will skip this slide because I understand we all know the availability of graph datasets in different domains and the application areas we have. But let me focus on the motivation for this particular work in detail, or in a kind of a focused perspective. So if we look at some examples such as image, text, and speech, we have very successful deep neural network architectures for these kind of datasets. And one thing is common is that all these architectures consider or kind of have inbuilt mechanisms to incorporate positional information. For example, coordinates implicitly encode spatial position. And there's a recent work in 2020 which shows experiments to kind of understand this aspect of CNNs. Similarly, recurrent neural networks, they build on sentences, build on sequences, so it has that. And transformers, they use word positional encoding. So these architectures have this particular thing if we view from the lens of positional information. So the question is, how about graphs, and how should graph neural networks incorporate positional information? In the ideal sense, if we have a graph with anonymous nodes, we should have a representation uniquely for each node, and at the same time, it's ideal or desirable to also have these representations distance aware. It means similar nodes would have similar features and distant nodes would have dissimilar features. So this is in an ideal sense we kind of envision. And if we have something like this, it helps distinguish, for example, simple graph pairs as on the top, this left and right graph pair. So all the nodes are similar in both of these graphs, and the popular message passing GNNs cannot distinguish these two graphs to be different. However, if we have a positional representation, for example, this is an example of the coloring brought by RWPE, which is the one which we focus in this work. I'll say about that in detail. But because of this RWPE, these two graphs can be differentiated, these two molecules, and this is what we want out of this work, or if we have a powerful positional information for GNNs. I'll now go through the background, three different research areas in graph representation learning. I'll just touch upon some selected works and try to present some things that we use or we highlight in building our current work. So first is the improving the expressivity of graph neural networks.
Before we go into that, can we maybe have a question?
Yeah, sure.
So if we look at the images,
yes,
that you have here, like these two images, it looks to me that it's very similar to the first eigenvector in absolute value. Like it goes from the strongest value here to like the smallest here and goes back to the strongest value. Is this something that that is observed in many graphs, or is it something you only observe when you look at these small molecular graphs?
Actually, that's an interesting observation. I didn't run experiments or show this coloring as compared to the Laplacian eigenvectors, but maybe that would be the case. In this particular case, it's just a fixed 5-dimensional RW positional encoding, and the colors are based on the unique RWPs. But it would be interesting to observe that. We didn't try to find its relation with the Laplacian eigenvectors, the absolute encodings. Yeah.
So in some sense, the Fiedler vector, so the first 1,0 eigenvector, is known to be correlated with random walks. So in some sense, like there are some papers about it, about even approximating it using competing random walks. So in some sense, this might be kind of the manifestation of that. And it would be interesting to see how it compares into different graphs.
I see. Thanks a lot for the connection. Yeah, it's interesting to explore on that line further. Do you have any other question in the chat?
No, but
okay, yeah.
Ahari asked in the chat, leave the question at the end. So no, don't hesitate to ask questions whenever you want to. Feel free to raise your hand or just speak up or send your question into the chat. Good.
Okay, let me continue. Yeah, so about the background. So these are the three different directions that we touch, and I'll brief about some of the selected things that is important to understand the context of the work that we did do in this paper. So the first is the direction towards improving the expressivity power of message passing GNNs. This is the most popular class of GNNs and has been, most of the papers and the implementations focus on this particular framework, the message passing framework. It allows pairwise exchange of information between local neighbors before updating the feature representation of a node. And because of this, it resembles similar to how 1WL algorithm operates. It's a classical test heuristic for distinguishing if two graphs are not non-isomorphic. So because of this alignment to 1WL, message passing GNNs failed to distinguish simple graphs that was also not possible to be classified with 1WL. For example, if you see on the graph at the right, this pair will not be distinguished by message passing GNNs. So to improve this limitation, we have seen in the last couple of years, there have been some development into making or developing higher order computation into GNNs, and it kind of mimics or emulates how KWL in the upper hierarchy of WL tests operates. So in the higher order computations that is being done in WL GNNs, it kind of mimics that K-tuple feature representation, and as a result, it can help distinguish non-isomorphic graphs that was not possible with 1WL, and the kind of alignment it brings is that a KWL GNN can help distinguish non-isomorphic graphs, which is also with respect to KWL, the algorithm for distinguishing non-isomorphic graphs. So this is how it's one way to improve the limitations of message passing GNNs. However, it comes at the cost of memory and speed complexity. And the good thing about message passing GNNs, it has its linear complexity with respect to the number of nodes if the graph is sparse, which is the most case with real world graph datasets. And because of this, in the recent times, more scalable and based on message passing GNNs, some hybrid methods have been developed, which is efficient because of the linear complexity, and at the same time make the models strictly powerful than 1WL. So this is one direction of improving GNN's expressivity and making it more powerful. The second research direction that we touch upon is graph positional encoding, and this is what we do. So positional encodings in GNNs help the network to disambiguate several node symmetries. It has been shown in that message passing GNNs, if they are used, if PEs are used, they can be more expressive, and even universal approximators if unique node identifiers are provided, among other sufficient conditions for this universal approximation. And one such unique node identifiers would be index positional encoding. So we just supply each node with with a unique node index. However, when we do that, there will be n factorial possibilities, and in practice, it's not possible to consider all that, and some sampling would be required. So this is related to. I mean, this is. Yeah, sorry.
Go ahead.
Okay. Okay. Sure. So
no, I mean that Shubham should go ahead.
Okay.
Sorry, I just muted him. I think maybe.
Okay. Cool. So I'll go ahead. So what are the desired characteristics that we should have for graph positional encoding? We have like 4. For example, the first is unique. We ideally require a graph positional encoding to have unique representation per node in order to like more align with that previous result to make GNNs more expressive. And then it should have distance aware information encoded such that nearby nodes have similar positional representations and far away nodes have dissimilar. Third, it should not violate the permutation equivalence of GNNs, and by design, the positional encoding that we have should be permutation equivalent. And fourth, it should be efficient and scalable to pre-compute or either to use in the networks that we consider. So these are the 4 desired characteristics. One possible candidate for graph positional encoding is Laplacian PE that we proposed earlier. And Laplacian PE is based on Laplacian eigen decomposition. And the Laplacian eigenvectors kind of embed graphs into a meaningful coordinate system. By design, it also provide unique representation and have the distance encoded information. This do not increase any cost of the computing the message passing GNNs complexity, because it's a pre-computation step and the eigenvectors can be obtained via the factorization of the graph Laplacian. So this Laplacian PE can be interpreted as a generalization of the PE that was used in the original transformers, which are the sines and cosines, as the sines and cosines would be interpreted as the eigenvectors of the circular grid in case of the original transformer. So this is one candidate, Laplacian PE. However, it comes with limitations apart from the multiplicities and due to eigenvalues. One thing that is important is that the eigenvectors are defined up to a sign, and when we are selecting a k number of eigenvectors, they can be 2 to the power k possibilities. So in practice, we will have to resort to some sampling, and in the past we have done random flipping while training to kind of sample from all the possibilities. And note that this sampling or these possibilities is still less than having a index positional encoding, because if we have index positional encoding, we would have n factorial possibilities of node identifiers. So this is about Laplacian PE and the limitations. There are also other positional encoding focused works that have been done in GNNs. First is the positional aware GNNs that consider anchor sets, and as a result, position aware representations are built, which are dependent or kind of tied to this anchor set of nodes and are used in link prediction tasks. The second is distance encoding, which are computed with respect to a node set, and this can be used either at the input layer with the node features or as kind of controllers of the message aggregation function. Similarly, we have random walk with restart used as topological embeddings for a GNN in consideration. So there may be other kinds of works also which try to incorporate some kind of positional information or topological information when GNNs are being applied. And in recent times, we have seen several works that use PEs to do transformers for graphs, which is the next research direction to be discussed. So
before we go on to the graph transformers, in the paper you mentioned a bunch of times how problematic it is to use the Laplacian eigenvectors as positional encoding, because we need to do the sign flipping. But is this actually like, why should that be such a big problem? I mean, it's just 2 times more. It could just the only disadvantage it could give us is that we need to train with 2 times more samples, right? Am I understanding that correctly?
Yeah, that's the, I mean, if for one possible addressal to this is consider all the 2 to the power k possibilities, but it would increase the training time, and it would be kind of a brute force approach to solve this problem. It would be similar to, for example, if we use all the n factorial node indexing, if we're using the index PE. So I mean, if the k is small, or if the data set is small, it's still possible to train on the graph data sets for the task at hand, but it adds to the computation, it adds to the training time. We may not be able to use all the possibilities for training.
Okay, but
and random sampling via sign flipping is one way to just select only a sample from that all possibilities, so that it doesn't add to anything extra to the cost.
Yeah, okay. So it's not that my statement that we just have 2 times more training time is wrong, right? Because
it won't be 2 times, I think.
Yeah. Okay, then let's get to your GNN transformers.
Transformer-based GNNs, yeah. So this connection of transformers in GNNs, I mean, we can feel it from the first work of graph attention networks in 2017, when attention was generalized for graphs by this GATS, and they used the attention for only local neighbors. And transformers can be interpreted as a special case of GNNs if we see the sentences as fully connected graph of words, because each word in the sentence will attend to every other word in the sentence. So this interesting connection has led to several recent works. And one generalization that we did last year was we generalized a graph transformer by focusing on 2 things. First, the positional encoding, because it is kind of extension from the words to the any general graph. And the second is the local attention. So being similar to the message passing GNNs, this architecture graph transformer, it is prone to the phenomenon of the information bottleneck that is critical. I mean, the critical limitation of the entire message passing GNNs as a whole. So one way someone can think is to connect everything to everything and use full attention. However, just using full attention directly may not work well without the use of appropriate positional and structural encodings. And this is what is being addressed in the recent several works. So in the recent works, for example, spectral attention, Graph-ET, and Graphomer, and several others. So this fully connected graph transformers is used in the presence of powerful positional and structural encodings. So spectral attention network is one such example where a transformer encoder is used on the Laplacian eigenvectors and eigenvalues to generate a fixed size PE. So this is seen powerful. At the same time, the model has, while doing full attention, the model has separate learnable parameters maintained for real and non-real edges. So these are the 2 things I feel makes the spectral attention networks very powerful. In the second model that was developed recently, Graph-ET, it uses the original transformer equations. However, the attention score is multiplied with some diffusion distance that helps to encode short and long range information. Similarly, in Graphomer, centrality encoding was used at the node inputs, and spatial and edge encoding were used at the attention score. I'm just highlighting these key things to kind of present this analysis. So all these three works can be seen to inject PEs at different levels in spectral attention network. Although it applies a learnable PE model, it's still injecting the learned PE vector at the node inputs. In Graphity, the PE is injected with the attention score, and in Graphomer, the centrality is with the node inputs and the other encodings with the attention score. So this is how all these different works are shown. I mean, they show that, okay, fully connected graph transformers can be very powerful actually, but in presence of these kind of positional encodings, if the network is supplied with. So hence, we discussed three backgrounds. First is the improving GNN expressivity, second positional encoding, and third transformer. So we try to build on all these different works to improve all these, improve these recent models and propose learnable structure and positional encoding framework, which I will now present in detail. So in standard message passing GNNs, the model perform node update and optionally edge update in this function format. I mean, in this form, which can represent most of the equations, most of the models. A node takes in its own features at a previous layer, and it takes the output of the message passing and uses in the update function to update its feature representation. If the positional encoding are used with the input node features, it can simply be, I mean, these are simply injected at the inputs by concatenating with the node features. So this is how the positional encoding are done. What we propose is we can actually learn the structural, we can learn the positional representation along with the structural representations at every layer. So we can improve this architecture with LSPE by simply adding these two steps. The first, we can have a positional representation update equation, which will be similar to how the node update equation is designed for a particular GNN. And then at every layer, we can concatenate the positional representation at the node update equation. So these are the two changes that we do compared to the standard message passing GNNs equation. And one thing to note is that the FH and FP would follow the same analytical function, which I will show in the demonstration in the next few slides. And if, for example, the GNN has an activation function ReLU for the node update, we try to resort to use TANH activation function for the position update, because it would allow to have both positive and negative values for the positional features that are learned as a result. And empirically also, we found TANH to be better than ReLU. So this fits with how we desire TANH to be used in FP. I will show how these things can be used in different kind of architectures in the next few slides. But I'll try to present first this architecture and highlight the key differences. I mean, in respect with how future GNNs can be used with LSPE. So the end-to-end pipeline is similar to how a message passing GNN works. There's an input layer where the available features are gathered. There's at each layer, the feature updates are taken place, and the output, the representation are passed to some loss function. So at the input layer, we have addition of the positional encoding compared to the message passing GNNs. It can be any choice, but the choice can be critical to how what kind of problems we are tackling. So at the input, the change is that we have a position initialization. At each layer, we maintain node structural features and node positional features. If you consider simply the standard message passing GNNs, each node only has the node structure features. However, we also maintain a parallel node positional features with each node at each layer. And at each layer, we have this positional update equation. And at the final layer, the final layer learned features for node structural representation and the positional representation are concatenated, and they're passed to the task loss. Finally, in a positional loss can also be used, which is based on enforcing the positional representation to kind of resemble the Laplacian eigenvector coordinate system. So this can also be used to tune the positional representation as well. So this is how this entire architecture works. And the key difference is just in this position update, the input initialization and the final using all these the node structural and the node positional features together for the task. So this is the main change compared to the message passing GNNs used in standard. What is the initial P? Yeah.
Oh, we have a question.
Yeah. So one of the innovation I think in this part is that the positional encoding stays separated from the network at every layer. So it forces the network to always think about the position of each node. Whether with other kind of networks, the position can be lost or squashed with kind of the rest of the information of the network. And because like in standard transformers for NLPs, the position is kind of trivial. So it doesn't really matter that this information gets lost across the network. But I think here in graph, one point that you're bringing is that because it's difficult to really understand the position and the structure of the graph, keeping this side network helps the network continue to always reason about its structure, right?
Yeah, exactly. And this is what happens. So this entanglement of these two different representations happens at each layer. And in practice, we found that if we simply use a powerful positional encoding as opposed to also learning and maintaining them separately, we always observe a difference in performance. So this is exactly the point you mentioned, that this don't get lost, and each layer it can learn separately and maintain it differently as compared to the simply node structural features. So this is what it's simple thing, but it makes the existing GNNs very powerful with this small addition to the network. Exactly.
Okay. But like now we have this additional network and concatenate the addition or inject it to the so to say to the usual GNN at every layer, the learned positional encoding. But what if you inject the your original positional encoding at every layer? Is that what you compare to, or do you compare with only injecting the original positional encoding in the first layer?
So if we simply inject the positional encoding to each layer, we performed experiments with, for example, Laplacian PE. It doesn't bring any difference in the performance. So if we add to the first layer and also to each of the layers, the performance is almost the same.
Okay.
Yeah, there's no any visible gain in performance. Yeah.
So this learned thing, this separate positional encoding network really gives us some performance improvement.
Yes, exactly. And I will show that later, that like the step by step, like how different components of the architecture help toward performance gain.
Yeah,
we'll discuss this towards the end, like even empirically. Yes.
But we also have in the chat the question, how is the positional encoding initialized in the beginning? But I guess you'll also get to your different positional encodings soon.
Yeah, exactly. That's in the next few slides. And I'll discuss about the initial positional encoding.
So before going to the next slide, I just want to bring another point that I find very interesting here, is that you said you use tanh as an activation function instead of relu.
Yes.
And this is very interesting because like people often don't think about which activation function, they just go with the relu by default. But here, the fact that you're using tanh kind of reminds us about what are the positional, what are the Laplacian positional encoding. The fact that a negative, that two nodes that have one is very negative and the other is very positive are far from each other. Whether if we use relu, we force the network to lose this kind of information about distance based on the sign of each node. So in some sense, the tanh is more works better with the Laplacian positional encoding, and even maybe with the structural positional encoding, because it allows this differentiation between nodes that are far apart, have different signs, thus they don't interact with each other.
Yeah, exactly. So I mean, like you say, it's kind of resembles that thing. And also if we simply imagine the position to be coordinates, just for a simple intuition, it helps to, I mean, the coordinate axis can be both positive sides and the negative sides if we use tanh, but that's not possible with ReLU. So simply using ReLU, it's not a good choice for the position update. And tanh is a very suitable choice. And in our experiments, we found that actually the performance is good when using tanh.
Do you have comparisons there as well? I didn't see those.
It's not in the paper or in this presentation, but we had that experiments done on the back.
Nice.
Like when we initially thought that it's useful to have tanh because to allow these positional coordinates to occupy both the positive side and negative side, and we used based on that intuition. But after that, we actually tried in the experiments, and the use of tanh was better than ReLU for the position update only.
Like, I understand the reasoning that Dominique or that Dom made with the positive and negative if we're using the Laplacian eigenvectors, but if we're using some other type of positional encoding, is that still the case?
Yeah, I think for any, because I mean at a particular layer, if we discard the input, if consider any particular layer, at layer L+1 we have certain representation. If we have ReLU, we would lose the negative information that is coming out from the previous layer, isn't it? For the positions.
Yeah, but can't we always say that in any neural network? Why is it special for the positional encoding?
Because I mean I don't have a very good answer to that. For like, I mean, why you use ReLU for everything, but I mean this comes because
I mean,
I guess it can create a sort of artificial clustering better than ReLU. But in some sense, ReLU could create clusters by putting one way that ReLU could deal with the sign is that it generates the positive and then the negative as two separate
values.
outputs, basically.
Okay.
Yeah, as two separate values, basically, like everything that's positive is in one box, and everything that's negative, it flips the sign with the linear layer, and then in the ReLU, it puts it in the second box. So in some sense, it can perform clustering like that as well. But maybe tanh is better suited for that kind of clustering. I don't know, like it's really
I mean, it's open in future. Like, yeah, that can be a good thing to explore, like different.
I think it all sounds so very speculative what we're saying here, but in the end, you tried it, and
we tried with ReLU, and exactly the tanh worked better, and that's the reasoning that we satisfied with. We got the intuition to satisfy for the particular reason, like why tanh is working better. But I mean, yeah, it's open. Like we could try any activation function for this as well. It's not very tight bound for this. Yeah.
But it's interesting how by now using tanh is an interesting thing, and like you have to how people wonder why you're not using ReLU. Yeah.
Yeah. Okay, so let me start with the positional encoding. Like, I mean, although this is general, like any kind of positional encoding can be used, but the choice of initial positional encoding could be critical in terms of like what would be the representation capability of the positional encoding. So if we use Laplacian PE, which can provide the unique node representation, it brings the limitations as earlier discussed, the sign limitations and all. So we resort to using random walk based PE based on the diffusion process of random walk. And we kind of, if we have a random walk matrix for a particular node, we select the value corresponding to the ith row and the ith column. That means after the computation of the random walk matrix at a particular step, we simply use the diagonals of the nodes of the matrix as the corresponding node PEs for the particular step. And we have a k-dimensional PE, which is kind of to the power of like the computation of the power of the random walk matrix, and it encodes the landing probability of a node to itself in 1 to k steps of random walk. So this results in a meaningful higher order structure information that I will demonstrate with some examples in the next slide. This RWPE is closely based on distance encoding from a previous work. And the difference with RWPE and distance encoding is that in distance encoding, there's a consideration of all possible RWIJ if a particular node set is considered. But in our positional encoding that we use, we just consider the diagonals of the matrix. So how is this a useful information? Because it provides a unique representation for a node given a distinct k-hop neighborhood if we have a sufficient number of k steps. So comparing with Laplacian PE, yes.
I didn't quite understand the RWPE yet. So if we go slide back there, this RW, this is now a matrix that is somehow determined by our graph connectivity.
Yeah. Exactly. This becomes a function of the original graph structure. The RW becomes, I mean, it's based on the original graph structure, and we have to the power 1, 2, up to k. After all this computation, we consider the diagonals, and for an I node, we consider the diagonal value corresponding to the ith row and assign it to the particular dimension of the PE for the particular node I.
But in the paper you write the RW matrix is the adjacency matrix times the degree.
The inverse. Yes.
The inverse of the degree matrix.
Yes.
So we kind of divide every entry of the adjacency matrix by the
degree.
By the degree. And why is that the landing? Like I would have, like if we just take the adjacency matrix, right, and we were to take powers of the adjacency matrix, then the II entry, so the entry on the diagonal, would be the number of walks that you could make of that length and get back to yourself. Is that correct?
Yes. So this, I mean, this helps to give a probability, like if the degrees, if a node has 5 neighbors and at a particular, so if in 2 steps it can come to itself in 1 out of 5. Yeah, I think I'm correct. 1 by 5. So that becomes the probability.
Okay. Yeah, good.
So it becomes a landing probability of a node to itself, the diagonal values.
Yeah, if you divide the values in the adjacency matrix by the number of connections they have, and then you're basically saying, yeah, now we're doing this walk, but we're walking into to every connection of our node with the same probability. Well, because we divided it by the number of edges it has. Okay.
Yes. No. So yeah, exactly. The notion is that it becomes a landing probability, and this is already, I mean, this entire matrix information was used as distance encoding in a previous paper, distance encoding related GNN for structural repetition learning. So this is already present there, and the difference here is that we treat this as a PE, and we only consider the diagonal values of this matrix. So it kind of becomes a low complexity uses of the matrix, and if we just use the landing probability of a node to itself rather than some neighbors, that's enough to be treated as a powerful positional encoding. And I'll show that how it works for distinguishing some graphs in the future slides.
Okay, so in this PIW PI P sub I top RWPE, this is a vector for every node. We generate this vector, and it is first the probability of landing on itself if we do a walk of size 1. So I guess it should always be a 0.
Yeah, I mean, if there's no self loop.
Yeah, okay, right. And then a walk of size 2, and then in the very end a walk of size k. Right.
Yes.
Then in the chat we also have the question by Fabrizio. Can you please expand a little bit more on what kind of higher order structure information this encoding scheme provides? But I guess that's what we want to show on the next slide.
Yes, exactly.
Okay.
Exactly. Yeah.
Then
So
let's
let me
go.
discuss about the characteristics. Yeah.
So I have a question.
Okay.
So so to start with, this positional encoding is going to be all positive.
Yes.
And your tan H argument about how does that come into play right now?
I mean, for the input, it's fine, it's positive, but when it's being multiplied with different learnable parameters we have for the positional representation module, it's not necessarily that everything will be positive, right? I mean, at the input only, it's good, it's all positive, but at each layer, it's also being processed with learnable parameters. That multiplication is happening. So it only helps there. And empirically, like we found that it's more, the score was more when we used tan H in this particular sense. So it does not lose that particular information that we discussed earlier. Yeah,
I'm fine with the empirical part, but yeah, I think the other part where it's the positive and the negative side, it's a bit dicey in my opinion. But yeah, if it's empirically it works, right? That's how neural networks work.
Exactly. So yeah, this activation should be, I mean, it could be this could be a thing to play later, like with different yeah.
And you also don't make any claims like that in the paper, right?
Yeah, it's not very tight. It's just that it's a choice that we used, and we found that it's a good way to use tan H there. Yeah. Okay. So about the characteristics of RWPE. So it does not provide unique, completely perfectly unique representation for each node. However, if two nodes are distinct in terms of its k-hop neighborhood, the representation of the two nodes is different. And why it's so, or sorry, how it's so is, if you consider two examples from zinc molecules in this particular graph, there are 24 nodes in the graph, and each node is assigned a different PE if the k value is 24. Because each of these nodes in this graph has a distinct k-hop neighborhood. However, in the right graph, there are 14 nodes and there are only 10 unique RWPEs. So it's visible from this top right and bottom right, like 3 nodes. It shows that, I mean, we can simply visibly see that the trend, I mean, after a particular length less than 24, this node and this node always have the same k-hop neighborhood. So as a result, these two nodes have the same positional encoding. However, this is the understanding of RWP. If there is a different k-hop neighborhood for two nodes, the two nodes will have different positional encoding for each of them. So this is the information that RWPE represents. I think it should be this should be well to understand the representation power of RWPE and how it helps to encode some kind of a very strong information of the original graph structure.
Okay. If we're talking about this RWPE now,
yes,
wouldn't we have more information if we didn't normalize, or if we didn't normalize it, so to say, every time, and if we instead if we just use the adjacency matrix and a power of the adjacency matrix instead of the random walk matrix, because then we kind of within each entry of our positional encoding vector, we also have the length, so to say, encoded.
I mean, that I don't think that would make such a difference, because it's just a normalization part that we're doing based on the decrease, right? I mean, apart from that, there's no any additional change in the two things. I think so.
I see that, but yeah, okay, no, that probably would make a difference.
I think it might, because I feel like it's the analogous thing would be sum based pooling versus mean pooling kind of a thing.
Maybe yes.
Right. So if you sum, then you get So I think that's could be the analog here.
Yeah.
So it should make a difference. I think what Hannes is saying might have more powerful might provide a more powerful representation.
Try it.
Yeah. I mean, we didn't try that, but it's interesting to see. Okay.
I'd like
Good point.
to
Good point. Yeah.
like to add on that, for example, if you have 3 nodes here, for example, what is the probability that a random walk starting here comes back to itself? Well, because this graph is quite simple, well, the probability will be 1 for this one, and it will also be 1, but it will not be 1 for this one. This one will be like 0.5, because at that point it will split into 2. But if you use the adjacency matrix itself, then I think you will. So this is if you use z minus 1a. But if you use a instead, well, the value that you get back here would be, I think it would be 2, and the value that you would get back on this point is 1. So in some sense, it gives the same information. Like, this is a very, very simple example, but in some sense, it gives similar information. It's just that in the end, one gives you the probability. So this one will give you the probability, and this one will give you the total,
some kind of
total of hops that bring you back to the original step.
The second one will give us the number of walks that exist from ourselves to ourselves with that specific length.
Yeah, and the first one gives you the probability of a walk going back to yourself.
Exactly. And so in the first one, we don't have the length encoded, so to say, but in the second one, we do. But then again, we kind of already have the length encoded in the position in which the number appears in our vector. So I'm not sure if there really is a difference there. Like if one does really capture additional information and it is true what we're saying with this, or this analogy with the mean and the sum is true. So maybe.
I don't think the analogy of the mean and the sum is true. Like, yes, in the case of mean and sum, the sum is clearly more powerful, but here here you can directly see with this very simple example, you can directly see that the degree is encoded in both approaches. In both approaches, the degree is encoded, but in a different way. So in some sense, like it's in some sense, it's clearly more powerful than just the mean aggregation. Now the question is there a difference? I would speculate that there's no significant difference between the two approaches, and even the probability would be more stable. Like, it will not explode for high degree nodes. The approach of using the total number of random walks would really explode for would give an explosion of value for nodes that have very high neighborhoods, especially when you do 20 steps random walks.
I personally think that there's no difference in the two. The nature of information revealed by both is the same thing.
I think so too.
Yeah.
Again, when I said there could be a correspondence, I didn't mean that it's a one-to-one correspondence between the sum and the mean, but I was trying to give, I think it has some kind of an extra information. But either way, it's not something that is clear anyway. But going to the other point where you point out that the explosion, I completely agree with Dominic that with the random walk probabilities, because its probabilities, the representation won't explode. But I think anything like this, especially when you're going to powers k, which are of the order of 20 nodes, you will only be able to apply it to graphs which are very, very small, right? This cannot be applied to a graph which has like 1 million nodes, because the moment you start doing random walks of size 24 on that, your method will fail to work. So I don't think we'll, again, given this can only be applied to small sized graphs, even if we take the adjacency matrix, the explosion won't really happen because you won't have that high, the node's degree would not be that big, right? All of the experiments you have run so far are on graph classification tasks, right? And these are all small graphs.
But even then, like doing 24 random walk steps, even if you have degree 4, it's 4 to the power 24. If all the nodes have degrees 4, for example, like it's like even if you take a tiny fully connected graph, has 4 nodes, all nodes are connected, doing a 24 steps random walk would explode that very, very quickly.
Even if we just had a chain, right? Wouldn't that be enough?
Yeah, it's again, real graphs are different from what we tend to like. It will never be a fully connected graph and all of those kinds of things. But yeah, there could be computational issues that you can run into. I completely agree with Dominic on that. But yeah, there could be a difference, but again, it could be possible that there isn't. For example, Dominic came up with an example where they are the same, but I'm sure we can come up with a counter example where we can show that they are going to be different. And then the question would be which one is better, but I don't think that's the point of the talk here. But yeah,
it's maybe not the point of the talk here, but I want to say that I don't think we can come up with a counterexample, but maybe we'll have some more things about that.
Yeah, fair point.
Okay, then
yeah, let's go on. Yeah, so this is what kind of information is encoded with RWPE, and as a result, it can help distinguish these kind of graphs, which was not possible with standard message passing GNNs, or like due to the one WL equivalence. So for this pair of molecules, simply having 5-dimensional random walk PE shows different vector for example, the node with label 4 on the left and the node with label 4 on the right. If you observe the numbers, for example, the values are the same till the 4th, and on the 5th it's different because the 5-hop neighborhood for the node 4 is different in both of these graphs. So this is important observation from this, and it also says that like when two nodes have distinct k-hop information, neighbor information, then it will be assigned a different PE, and consequently these two graphs will be distinguished by this RWPE. On the right, it's an example from circular skip link graphs. So here, this is important to observe that in a graph, all node will have the same PE. So it's perfectly not unique. It's not unique at all. All the nodes in a particular graph will have the same PE. But if we consider two different non-isomorphic classes, the P's are different. So this eventually helps to distinguish this graph classification problem in the circular skip link dataset. So these are the examples to help understand, like, although it's not perfectly unique as Laplacian PE, the RWB can have very meaningful information, and it can identify these kind of graphs which are failed by one WL, and thus establishing that its representation power is strictly powerful than one WL. And at the same time, we don't have any sign ambiguity for the network to learn or to do this sign flipping as we did with Laplacian PE. So this is about the initial positional encoding that we use RWPE, but at the same time, this choice with the architecture is open, and in future, any different kind of experiments can be done with the PE, keeping the entire framework intact. So next, we show in a work that this LSPE can be used to enhance any kind of message passing GNNs, either sparse or either fully connected. So we try to instantiate two examples of both sparse message passing GNNs and transformer fully connected GNNs. So in gated GCN is one of the instances we consider. We simply add these steps. We have a positional encoding update function, and we have this concatenation step for the node update equation. And we have a gate addition LSPE. So there's very minimal change that we have to do. And note that we have tanh in place of ReLU for the position update. For the PNA, we also do the same thing. We simply add the positional update function, and we use these concatenation steps. And when you note these two differences, you see that we can use the same function. How the GNN uses the instantiation of function, update function, message function to compute node representation. We can use the same kind of nature of function in the position update, in gated GCN, as well as the PNA. So it's very much open to experiment with these kind of things, and we try to use. Yes, Hannes. Yeah, sorry.
Any specific reason for the batch norm?
Yeah, I mean, experimentally we find that the batch norm doesn't help.
Okay.
For position representation. Yeah. So I mean, yeah, it's an open thing to explore further, but in our experiments, the batch norm didn't help at all. Yeah, for the position update. So this is the sparse message passing GNNs with the instantiation of LSPE. Now we use this to recently developed fully connected GNNs, and we as same with the sparse GNNs, we have a position update module and the concatenation of the position for the H update equations. And for Graphite uses this. Graphite has the same equations as a normal transformers, but it uses the diffusion distance for a pair IJ to improve the attention score. So for Graphite with LSPE, we try to modify the architecture with this. At the same time, we also use this separate parameters for real and non-real edges and modify the width score using this. So we try to follow SAN and Graphite, but we perform minor modifications to have the best possible base architecture and then compare with LSPE. So the details are in the paper for the complete equations, but with this 3-4 slides, I wanted to show that how the LSPE can be used with any given architecture, and we have to make very few minimal changes, and we have a network which can separate this position representation learning. So if there's no question, I'll proceed with the numerical evaluations now. So first, I'll show that this empirical evaluation of how different components contributes to performance gain. And for this example, we consider one model, gated GCN LSPE, dataset zinc, and we observe the metric, how it's performing for this particular experiment. So these are the 8 different kind of experiments. In the first 4, 1, 2, 3, 4, we don't use the learnable position representation. We simply use the original architecture, and we try to see the effect of having different types of initial positional encoding. And in one experiment, we also see that if we simply shift the PE from first layer to last layer, what's the effect? So these are the things that we observe. First, the positional encoding is necessary because it improves the performance. Second, RWPE is significantly better than using Laplacian PE. Third, the use of PE at the first layer is important as opposed to the final layer, because then since the first layer, the model is aware of how to like distinguish different symmetries when aggregating different node features during the message exchange. And now when we use this learnable positional representation, we observe that with RWPE, it first of all, it tries to, I mean, it leads to, first, if we see simply the row 3, there is a performance improvement, but at the same time, there's an overfitting. So the train accuracy is also, train score is also very much overfitting on the, it leads to overfitting on the train set. So when we compare row 3 with row 7, row 3 with row 7, you can see that the row 7 helps alleviate this overfitting. So from 0.013, it reaches to 0.018. So, and at the same time, it improves the generalization performance from 0.0 0.122 to 0.100. So then it shows that if we have the positional representations updated at each layer, it can better help tune the representations for the task and alleviates overfitting. And finally, at last, we select this architecture where we have a given GNN, the RWP as the positional initialization, the learnable positional representation at each layer, and then at the final, we fuse the learned representation from the last layer and pass it to the task. So this is the final architecture we select in our main experiments. These are our experiments on all the different data sets. We consider 3 molecular data sets for our main experiments, and we see a consistent enhancement of performance of all the 4 instances, gated GCN, PNA, SAN, and graphite, when we use the Learnable positional encoding. In all the 4, we see that the performance of the base models is increased by significant and considerable margins. And it's the similar trend is also observed with TOX 21 and PCBA. We always have enhancements when using LSPE. When we compare sparse GNNs, the gated GCN PNA, and the fully connected GNNs, the SAN and the graphite, we show that we observe that the sparse GNNs are better, and it's also very efficient, because if you see the per epoch time, all these experiments are performed on the same machine. So the per epoch time for a sparse GNN is better than compared to a fully connected GNN. And for the positional loss, we tried several experiments, but we only found improvement for positional loss for zinc, and it doesn't improve for other data sets. So it's still it could still be a area for further investigation of the positional loss. It improves the trend score, but it only improves the test score for zinc and not for others. So these are the main experiment results for the LSPE. And comparing to the baselines, domain agnostic, yes.
Let's maybe get to the previous slide and have the questions there first. A lot of stuff.
Yeah. Okay, sure.
Dom, you were first. Let's go.
I just want to ask whether you use the random walk with the Laplacian together and see if that helps.
No, it doesn't help. Yeah.
No, it doesn't help, or no, you haven't tried?
Oh, no, we didn't try with the combinations of both.
Okay.
Yeah.
Okay, thanks.
Because I mean, we would have to then perform some sign flipping on half of the vectors. I mean, if we simply concatenate the two, there would be this choice to make. I mean, it's a simple experiment to do. Yeah.
All right, that's it for me.
Okay, sure.
Fabrizio, you can go next.
Thanks. Yeah, it's a quick one. Sorry if it's already in the table, but it's very big, so it takes a while to parse it. So I was wondering what happens if you use PNA with initial positional encodings, say RWPs, but without updating them through the network. Because what I was wondering is, in principle, PNA is a provably expressible, provable expressive architecture.
Okay.
So in a sense, somehow, this network could learn to let's say, retain the initial information from the positional encodings rather than, through the network. So you don't need to inject it at every layer and learn it and so on. So in principle, you can, if this is expressive enough, and PNA should be, expressive. My hypothesis was that, well, at the first layer, the first layer can simply, learn to make use of this information, retain it, and then the next layers will still make use of this information. Maybe to explain it better, like
understand. Yeah, understand this. Yeah. So I believe like the use of RWP, but no LSP is what you're referring to.
Yes, exactly. So, well, let's not even talk about the probably expressive, but let's say that if you have an architecture which can learn injective functions, so the aggregators can be learned to be injective, right? So the initial information could in principle be retained through the network. So I was wondering what happens in this case. So I guess probably injecting the information at each layer is still useful, because maybe it helps in the training for some optimization reason, or maybe because of generalization. But I was wondering if you have tried to run some experiments specifically on this.
No, we don't have the experiment for the ones you are referring, but I think the Learnable, I mean, from the preliminary results, the Learnable thing was still helping. For the PNA, it's an interesting point that you made. Let me. I mean, I'll maybe try to work on this later, or kind of experiment if it's help. But we think from our preliminary experiments, the tuning it helps, because yeah, for example, if we simply consider this 7 and 8, the positional representation that are passed after the learning, it helps a model. But then, yeah, it's gated GCN and not PNA. So that would be a different, I don't know. Yeah. So
yeah. So I'm not familiar with gated GCN,
yeah.
so I'm not sure it can probably learn injective functions. If the aggregators can probably learn injective functions. So that's why I was referring.
Yeah. Thanks for raising it.
More
Yeah.
expressive.
Sure.
I mean, it's just I would be curious to see what happens. Maybe you still get some improvement because you have a better bias, and it's just easier to. So the network can, for example, focus on learning other important things rather than learning how to, retain this information. So maybe it still helps. I was wondering, if this is verified in practice or not. But yeah, that's it. Thanks.
But then at the same time, I think having learnable positional encoding, it doesn't make any harm, isn't it? Like, for example, if we have the positional encoding and then we're learning the positional representation, we still have a way to not affect the model in the model's representation capacity, or the what I'm trying to say is, I don't think it will having this particular line as opposed to not having learnable positional encoding and only the input, I don't think it will be a better performance. I mean, just from speculation. Yeah.
Yeah, I was wondering if it helps in practice or not. Like, yeah, I wouldn't expect better performance not using.
Okay. Yeah, nice
Learnable.
point. Thanks.
I mean,
A
it
lot.
always depends on the data set, how many data you have. I mean, it's very hard to predict these things. But yeah, the thing is, there are many factors involved here. So there's not only the fact that you kind of have the positional encodings at each layer explicitly into the basically injected at each layer. You also have the fact that you learn them. So there are different factors, of course. So it would be interesting to make finer ablations of this kind. I believe.
Yeah. Thanks. Yeah, it's an interesting point. Yeah. Okay, so we're almost at the end, and like the comparison with I mean, I think this is enough to show the improvements with the proposed idea of having different parameters and different modules to update positional and structure representation. And it also shows that, like, comparing with the existing models, existing baseline models and domain agnostic GNNs, we observe we improve the existing scores on Zinc and TOX21, and for PCBA we achieve, like, with PNA with LSPE is very close to the second best DGN on PCBA. So yeah, but I mean, we couldn't try DGN with LSPE, but it's a possible thing to see if that improves the performance of DGN, and even PHC GNN. So I mean, there's endless number of experiments that we could be done still for PCBA, but it's a good data set in terms of its size. The number of graphs in PCBA is large, and that's one thing that would be done in further experiments. So to present with what are the things that we learn from this this work is first the decoupling and learning of structural and positional representation at every layer. It improves existing GNNs, both sparse and fully connected. Second, although the PE can be any choice, its initialization is critical and contribute greatly towards improving the performance. Third, LSPE helps the feature representations to be tuned for the task and improves generalization in general. And fourth, compared to the fully connected transformer GNNs, in our experiments on the datasets we consider, the sparse GNNs perform better on the molecules. Finally, this architecture can be used with any GNN model that fits into the message passing framework, and with minimal changes, we can have a network that learns positional representation at each layer. So thank you very much. If there's any question, we can discuss still. Thank you.
Well then, thank you for the awesome presentation, and especially for your nice answers and a great discussion. And for the great discussion, I also have to thank all of our other participants, because yeah, thanks Vijay for the nice comments. Thanks Dominique, thanks Fabrizio, and thanks everyone else. Cool. But any other questions about the paper?
Well, I just to add, I would have loved to give the example, but to give a quick summary of why it cannot be the same, the two things, why using the adjacency versus the random walk matrix. If the powers of the random walk matrix and the powers of the adjacency matrix scale the same way, then they would be the same thing, right? If because they're going to scale in a different way, that's why they are not the same matrices. Otherwise, they'll be more or less just scaled versions of each other.
Yes.
Yeah. So that is why obviously at some point you will start getting counter examples that these two embeddings are not equal. So if you, instead of taking a 3-chain, which was the example Dominic gave, if you try a 4-chain and you look at the embeddings, already at the second position, you'll start seeing a difference between the random walk embeddings, positional embeddings, encodings versus the adjacency based positional encodings. So yeah.
You say you start seeing differences, but the question is not whether we see differences, but whether it can distinguish nodes that have different nodes that are different in some sense. Like if the graph is perfectly symmetric, then there's no difference between two nodes that are at the same position but with the symmetric graph. And the question is like not whether they will have different embeddings, but whether both the random walk and both the power of the D-1 matrix, the D-1A matrix or the A matrix are able to distinguish nodes in both cases. I don't know if my comment is clear.
Okay, yeah, that kind of makes sense. To do that kind of a comparison, I think I'll have to go into more details, but at the very basic level, the embeddings will start changing for obvious reasons. But yeah, if because of those embeddings, we are able to distinguish between the structures of the graph is a different question altogether. I agree. I completely agree with that.
And to that point, Muhammad has put in the chat that random walk will fail to disentangle co-spectral non-isomorphic graphs.
Yeah, it's correct.
And it's less powerful than 3WL. I think I've seen some work on that, but like it's more about, I think this is some question that spectral graph theory can help answer.
Yeah, I think, I mean, it's indeed like the RWP doesn't help for any K, it doesn't help to distinguish the non-isomorphic graphs, because I think co-spectral non-isomorphic graph. I think there's a paper which details kind of a matrix language which sees this in terms of the number of operations, or sorry, the nature of operations that a particular 1, 2 WL, 3 WL, KWL networks they kind of emulate or they kind of do. So it doesn't, RWP's representation power in that respect is lesser than 3WL. That is correct.
Yeah, he also wrote into the chat, it's not lang work.
Yes, matrix language. Sorry, yeah, matrix.
Okay, then maybe what's your estimation on the future of graph transformers if we're looking at these insights on positional encodings?
I think there's still open questions because maybe at first we may not have good data sets to evaluate transformers on graphs. Because if we, from our experiments, we see that if we kind of have a good positional representation kind of model for even sparse GNNs and they're efficient, we may not need transformer GNNs for the small molecular data sets that we consider, the different graphs of small graphs. So the first question on this line is like, do we have or what kind of data sets we should evaluate transformer for GNNs and where are actually they useful? And the second thing is like, if we consider large graphs, we may not able to naturally proceed with doing full attention because it would take time, and maybe for going after a few K of nodes, it would be very prohibitive to fit on the memory. So that's the second question. I don't know how it goes, but I still am very open to explore different ideas on these kind of lines.
Yeah. And then one question. Okay, so yeah, the transformer way, the transformer direction is definitely interesting, and adding position, or we kind of need the right positional encoding to make the transformers work, because, well, they don't have any notion of the graph unless we give it to them somehow. But in theory, we have this, we're no longer constricted now by this hop neighborhood or the number of layers that we have, the number of message passing layers that we have. So we kind of wanted, or I kind of wanted to work. But then about positional or the future of positional encodings, do you think that Laplacian, using the spectrum of the graph Laplacian has a future there, or do you think stuff like the random walk positional encoding, or maybe using the personalized page rank score as positional encoding is more promising?
I think I don't have a particular answer to that. It would still depend on how we sort out issues with the Laplacian eigenvectors, for example. It sounds very interesting to use, and given the properties that it brings, but I don't have an answer like how it proceeds. And at many of the times, for example, there was a recent spectra transformer, for example. They show that there's for different data sets and for different model settings, they don't find a consistent choice of positional encoding for all the data sets. So it's very hard to say at this point, like what's one answer to positional encoding, which one to use, the random walk based or the Laplacian PE based. It's very hard to say that, I think.
I was just thinking this, the paper that you presented, what you call it, graph IT. I'm not sure if they call it graph IT or they call it graphit.
Okay, yeah,
I
haven't had as well. Yeah,
I think it's French, or should be kind of pronounced in a French way. Okay, but they do a really rigorous comparison of these different positional encodings, right? But when injecting them into the attention scores, and they compare like page rank and some other diffusion processes, and then they also compare with some more discrete encoding, so to say, that go into the direction of your random walk positional encoding. And they also find that these work better than the nice, so to say, the nice principled methods like personalized PageRank score. They don't work as well as the random walks or doing something like that. So I think maybe there's just some, maybe there are just some encodings from which it is easier to learn, so to say. So even though, for example, the Laplacian eigenvectors contain all of the information and are super nice in theory, maybe it's just not so easy to learn from for
Yes, maybe, yeah, exactly. The model, it may be hard for the model to learn the invariances because of the limitations brought by it. Otherwise, it sounds very good to use intuitively.
Yeah, okay.
I would like to jump in here.
Yeah, perfect.
To say I defend the Laplacian positional encoding. So one of the things is like it depends also what kind of GNN you're using. If you're using a transformer and you're using only structural positional encoding, like I mean a fully connected transformer, the structural positional encoding will not inform anything about the distance. The diagonal of the random walk will not inform anything about the distance between two nodes. So then you have two options. Either you use a transformer where you use also the non-diagonal elements of the random walk to give you a form of distance between each pair of nodes. And this looks a bit like how Graphomer did by taking the shortest path. Or you are forced, if you stay on the nodes positional encoding, then you are forced to use Laplacian positional encoding as a way to allow the transformer to determine whether two nodes are far from each other. So in some sense, like if you stay on the node-wise positional encoding and not have it as a relative position, as a relative distance, then you have no choice of using some kind of asymmetric positional encoding, like the Laplacian.
Yeah, but why are you saying that we don't have some sort of encoding of distance? We have that as well, right, with most other positional encodings.
Well, not if you take, for example, the diagonal of the random walk, or even any kind of node information, for example, that depends on its structure. If you then fully connect the graph, then two nodes will not be able to understand whether they are far or close to each other. But with the Laplacian positional encoding, then even if you have the sign ambiguity, it's very easy for the network to say, well, if the signs are different, then they're far from each other. If the signs are not different, then they're closer to each other.
Yeah, okay. Yeah, with the random walk or diagonal of the random walk matrix, we don't have it.
Yeah, but when in the paper sorry, just want to finish, then you can go. In the paper which I presented, gated GCN and PNA can know if two nodes are far apart because they don't get the aggregation from them, you know. So it's really a problem of which architecture you use. Sorry for interrupting.
Yeah, I think I agree with your point. Like the difference comes with the sparse aggregation and the fully connected. And for the random walk, if we don't have diagonals, I mean, if non-diagonals, even if we are just computing or just using the diagonal information to have RWPE, it still encodes some kind of distance information, right? I mean, although converting it ultimately to an absolute positional encoding because of the diffusion process.
Yeah, it encodes a general structure. The diagonal will encode kind of the structure and the general distance it has to other neighbors, but it will not encode whether, if you fully connect the graph, it will not encode information about whether node A and node B are far from each other.
Okay, I get it. Yeah.
Okay, but then no, let me go with another question on the positional encoding stuff. So you also presented your positional loss in your paper, and you also wrote, we will investigate a more consistent positional loss in a future work. So do you think that's a promising direction?
So I think there are a couple of works that are absorbed in this direction. So, for example, there's a paper, Dirichlet Energy Constrained Graph Learning. So because the Laplacian eigenlaws has two terms, the Dirichlet term and the orthogonality term. So there was a paper, if you Google, like, or maybe I'll send later in the channel, Dirichlet Energy Constrained Graph Learning. So it tries to constrain in a bound, lower and upper bound, the Dirichlet energy of each of the layers of a particular GNN in consideration. So we are trying to enforce by the help of graph structure by using this Laplacian eigenvector laws, but maybe it requires a further investigation, and there are actually the works on these kind of lines. For example, the one I mentioned that is trying to do that, and it maybe it will come in a later further exploration. Exactly.
Okay.
Yeah.
I'm looking forward to all of your future explorations. But then let me say thank you one last time for your awesome paper and the awesome presentation.
And yeah, thank you very much. And there were some very interesting counter comments and also the examples that I think it's very important to think on these things. For example, this very simple, but the random walk and adjacency matrix discussion, and also the PNA. So I got really good feedback from the discussion, and thanks to everyone and for joining and engaging.
Okay, another awesome presentation, lots to learn and great discussions, and the spectral attention paper that we mentioned during the presentation, that was actually also covered in a previous reading group meeting of ours, and you can find the link to the recording of that in the description. Also in the description there are all the links to follow us on social media, to join our Slack channel, or to sign up for the mailing list, such that you never miss out on another meeting.